Okay, the second speaker is Noam Preil, also known as Pixel Hero Dev. Noam is from the US and he studied electrical engineering. His talk is about a compiler toolchain he's working on, and if you're on Discord the last couple of days, you probably already know a lot about it. The talk is Project Tricarbon. Noam, the stream is yours.
Right, so before I can get into the actual project, I wanted to explain the motivation behind it, and to do that, I need to explain why I had problems with all the existing tool chains. A key goal I had was that it should be usable for both compilation and emulation, not just one, not just the other. GCC, for instance, and LLVM, they have a JIT toolchain. You can use them for emulation, but they're not very good for it. So there's a lot of shared code between the two. It shouldn't be wasting any efforts. Every feature needs to have a justification. I don't want any extra features, nothing that isn't 100% needed for what it's doing. No two features should cover the same scope. Nothing should be necessary. Every single line of code should be there for a reason. Generated code has to be fast, but so does generating it. So if you generate the most efficient code ever, twice as fast as GCC, but it takes you 2 years to do it, it's not worth it. Clients should have full control over every single step of the process, so if I'm writing a JIT and I want to tweak some random internal, I should have the ability to do that. I shouldn't need to worry about it not being marked public. Completely arbitrary backends should be usable, whether that means something like a Harvard architecture with separated RAM, ROM, a system with no registers, a system with only registers and no memory, whatever it is, it should be supported. And it should be completely modular. Every piece should be able to work on its own. They should augment each other instead of depending on each other. LLVM is not particularly great for these purposes because while the IR is actually really good, the library is less so. It's just a whole bundle of C++, which might not be a problem for some people, but when you're trying to work at a different level, for instance, in Zig or in C, it's very annoying. They have bindings, but it's very clear that non-C stuff is not that non-C++ projects are treated as second class. And while the produced code is pretty good, the compile time performance is not. Weird backends are very annoying to add, and of course, it's not written in Zig. Is definitely a problem with it, definitely part of the motivation. It is usable for emulators, but only technically, and as everyone knows, any sentence that begins with technically can just be ignored. It is nowhere near simple enough for my purposes, and while it vastly exceeds the runtime performance goals, that's just one factor. Compile time is awful, and the performance at runtime is not everything. The same way I like to say that safety is not the most safety might be a very important goal, but if you have the most safe project, but it's not able to run at more than one instruction per second because it's constantly checking unnecessary safety features, and it doesn't matter. It needs to also be able to function properly. Similarly, here, compile time performance is also very important, and meeting one of the factors is not nearly enough. While the libraries work at the C++ level and there are C bindings, it is unnecessarily difficult to integrate with other projects. QBE is better, but it's not quite there. It's also less well known, so I'm just going to give a quick rundown. The goal of QBE is to have 70% of the performance of LLVM or GCC in a tenth of the code. It's able to compile in half a second even on older hardware. Currently, it only supports AMD 64, nothing else. It's written in C99, but the actual C library isn't there yet. It's hackable, which is good, and it's much easier to work with. And honestly, I probably would have just worked on QBE directly instead of doing my own, but that would probably have been less fun. And I had some differing design decisions also. It meets the goals of performance and simplicity for both compile time performance and runtime performance. I do not believe it is usable for emulators out of the box, though that could probably be fixed. Platform support is, of course, poor, and just like LVM, it's not written in Zig. No breaker there. So my solution is I'm going to make my own toolchain from scratch. This will end perfectly. Sorry, this is definitely not going to exacerbate the issue in any way. I don't see why anyone would think that. Some of the key ideas behind the Project Tricarbon stuff is that emulation is a first-class use case. It's not just a side point. It's not just you can use the same stuff. It's there. It's a key goal. It should be just as nice to work with for emulation as for compilation. There should not be any duplication anywhere. The components used for compilation and emulation should be the same. Backends should not have duplicated code, but should share common components. And it should be, at least to some extent, provably correct at compile time. It should be able to prove that the final binary matches the source code. This is arguably a trusting variation, because in order to be able to prove that, you have to prove that the compiler which is used to produce Tricarbon is itself correct. I'm ignoring that because that's not relevant. Should not do any work it does not have to. So if there's an optimization that buys like 0.01% performance, there's no point in doing it. Don't even bother. If there's some step in the process that can be eliminated and replaced with something simpler, don't do anything that's not completely necessary. Quality of the code matters, not the language it's written in. I'd rather have high-quality C code than low-quality C++, and vice versa. I don't care what the language is, it just does not matter. One rule is that all of them have to share the same ABI, and because this is the current C component from the last decades, it has to be the C ABI. Whether that's the system v1 on POSIX or the MS Build one on Windows, they have to speak the same ABI. This means that if you're writing in Zig, everything has to be exported. You have to have the exported API as the priority. And for C++, everything needs to be marked extra in C, and so on. It also should be able to handle completely arbitrary IR formats: ZIR, QBE, LVM, and so on. All of them should go through the same pipeline without any changes, which should be able to convert them into one common format using a generalizer. Some of the inspiration was Lefticus's 86 to 6502 transpiler. I stumbled upon this at one point a year or two ago, I think, when I was working on a Z80-based emulation system. And I made the mistake of trying to port it to Z80 instead of doing one from scratch. It was a mistake. But it stuck around in my memory for a while. It's an interesting project, able to compile C++ as the 6502 using GCC or Clang, and just translating the assembly itself. Another project that I drew a lot of inspiration from was MIR, or the middling IR. It's basically the same thing I'm doing, or QBE is doing. It's an alternate tool chain from scratch, except MIR is a lot closer to what I'm doing. They are planning on, for instance, parsing LVM and using that directly, so on. One of the things I learned from that is that disabling optimizations in GCC or LVM for JITs just does not help, because the time for it to assemble an empty file is simply too long. Oh, there we go. On an Intel something or other, i7-9700 or something like that, an empty file takes nearly 8 milliseconds to compile with optimizations disabled. Turning them on doesn't really change that. Level is not enough. The initialization time is the problem. It does not matter how quickly you can run after the initialization if translating a block takes this long. It's just intolerably slow. A quick overview. Cross-compilation is a first-class use case, which you might recognize from the Zen of Zig, or maybe it was the Ziglang website. Either way, all compilation is treated as cross-compilation. To achieve that, I'm using RISC-V as the IR. Not directly, or not the first step. It takes in, like I said, LVM or QBE, generalizes that, and then does some basic work on that and produces the RISC-V IR. Then this is used for the rest of optimizations, translations, and so on. A custom RISC-V quote-unquote extension is used to provide fused operations, but I put extension in quotes there because it's not really technically a RISC-V extension. It's more like it's treating multiple instructions as a single one in memory. If it actually writes it out as RISC-V, it still produces completely canonical RISC-V machine code. There is an actual custom extension used for instance, register sizing. So RISC-V, I'm using a 32-bit RISC-V base, which means that all instructions operate on 32-bit registers. There are only 32-bit registers. It's not like 86 where you can access them as 8 or 16-bit components. They're always 32-bit. To make CodeGen more efficient, what it does is it allows for certain instructions to basically say, from now on, treat this one as if it's smaller, which means always assume the top bits are zeroed because we're never going to let them be set. Which this can be used to optimize in various different ways, but it's also just it's more efficient. No, like I said, don't waste any work. So yeah, front ends only have to target a single backend. So if you're writing, for instance, a Zig front end or a ZIR front end, it only has to target RISC-V. You don't have to target AMD 64, ARM, MIPS, and so on. You only have to target a single one, which means writing that front end is easier. And one analogy I like to use here is consoles versus PCs. Consoles aren't better than PCs because they have better hardware, though they often do. They're better because they're 100% consistent. Every single one has the exact same hardware, which means that if you're writing a game for it, you can optimize specifically for that hardware, and it does not have to work on anything else. It's the same thing here. The front ends do not have to worry about anything other than the RISC-V. That is it, which means that they can do more efficient output there. And then the RISC-V can be proved to be correct. Basically, if you can prove that the RISC-V matches the input IR, then you can prove that the output, the final machine code, for instance, this 64-bit AMD 64 machine code, is exactly the same. The IR can also be manipulated using common tools because RISC-V, there are just RISC-V tools out there. You don't need to make new ones. And register allocation when writing an emulator is effectively a knob. It is cheap, it is easy, it is simple. You don't even have to worry about it. And translation's pretty simple too, especially for RISC like ISAs, but even for other ones. So yeah, it's also easier to interpret the RISC-V than to try to interpret LLVM-IR, for instance, because it's an actual ISA and it is completely interpretable, whereas this is not. So this allows to prove that the machine code that is correct. The IR can be interpreted while running the final machine code step by step the same way GDB would, and you can prove that the high-level variables are the same. It's not about checking the registers or anything like that. It can say, okay, we can map a variable in the source code to this register on RISC-V and to this spot in memory on the AMD 64 code. So let's just test the values after every instruction that modifies them, make sure everything is exactly the same. And that's where Thor comes in. Thor is one of the Tricarbon components. It translates RISC-V to arbitrary backends, currently AMD 64 only. And yes, I know I complained that QBE only supports AMD 64, but the issue there isn't what it supports now, it's what it can support in the future. QBE is explicitly designed for AMD 64. There's ARM support is planned, but that's it according to the website, and that's just not enough for me. So Thor is also designed to support, for instance, the Z80, which is an 8-bit ISA without any issues, without needing to change anything that's done. This is one instance where register sizing comes in. If you can say all these registers are 8-bit, you don't have to worry about the upper bits. You can treat the data as the correct size. To allocate the RISC-V registers to host ones, it uses a linear scan register allocator, which basically means it goes over the code from the RISC-V from start to finish, and it makes a list of which registers are used when. So what it does then is it says, okay, this register is needed from point A to point B, this other one's needed from C to D, and then it just allocates a register to each. If it whenever that interval, that hive range is over, it frees up the host register so some other value can use it. And since currently the target is AMD 64, which has about 14 usable 64-bit registers, unless you're using 14 values simultaneously, you're not going to run out. For other systems, it'll have to do, for instance, register spilling, moving them into the stack before you use them again, but that's not the concern for just yet. The reason I went with linear scan allocation is that it is vastly simpler than the graph coloring method that is used by GCC and LLVM. Which means that the performance when running the allocation is much faster, significantly higher, which means improved JIT time, and for most compiled code, it's going to be just as fast too. Another component is what I'm calling now the unnamed backend project, because I originally named it Lightsing as a pun on the new Lightning project before realizing that was a terrible idea, and using a joke name was not a good long-term option. So yeah, it's temporarily nicknamed Lightsing because I'm a horrible person, but Lighting did a better job with the pun because or Lightning, was there an EN in there? Either way. So eventually, it was originally part of the same project as Thor, but I eventually split them apart because each one has a narrower scope now, and they're more modular. If I want to write just a raw 64-bit assembler, I can just do that without needing to worry about the other components. The backend works is it has an instruction builder that creates a list in memory of what instructions are there, and it determines the sizing while building them. So it basically decides which variant of an instruction to use ahead of time. It also processes labels correctly, so you can give it labeled code and it will work. Unlike Felix's two-pass assembler, the way this one works is just single pass. When it creates a second list of labels and a third list of references. So the assembler basically creates an in-memory object file, an object file-esque structure, which has the references, the labels, and the actual instructions. There are no optimizations performed by this whatsoever. Those are done at a higher level. Those are out of scope. It should be as simple as possible. If I want an assembler, I don't need it optimizing. I'll do that myself, or I don't want to do it at all. There is no real linker, and that's a design decision. Like I said, it's out of scope. Don't add any unneeded features. So when compiling a proper if you're compiling a multi-file source input, like a 10C file project, you're going to need an external linker. You can, however, if you have like a single file the way Zig does, you're not going to need one anyway because everything's internal. There is a mini linker which can resolve internal references because it has the list of labels and references, so it's able to match them up and just trivially replace them. This is useful for JITs and for single file compilations, and it's much simpler to implement. I think it's literally like 15 lines of code at most, which is nowhere near the complexity of a proper linker, which means that it can have most of the effects needed without the costs. Some potential ideas for the future were hot-swappable register allocators, similar to the way that Zig is planning an optimized for built-in. So you can say, I want this to be fast, I want this to be safe, I want this to be whatever, I want this to be small. You should be able to say, well, I want this specific bit of code. It's going to be a very tight loop. I need it to be the generated code as optimized as possible. The compile time here isn't as relevant because it's going to run a billion times and only be compiled once. Or you could say, this bit of code is literally only running once. So you know what? I don't even need a register allocator here. I'm going to use adaptive optimization. Instead of, for a JIT specifically, instead of actually translating to the native architecture, it can, in theory, interpret the RISC-V directly, producing the correct results. This is, I believe, something that Hotspot JVM does and other projects. It means that you only use the JIT where you have to. Another idea I had was for a Linux package manager, which uses the RISC-V IR as the binary form, already optimized. Everything statically linked, tracking dependencies, solely relinking whenever a library is upgraded, which removes the single biggest problem that people have with static libraries, if I remember correctly. And since the RISC-V that shipped is already optimized, the only optimizations that you need to perform when it's installed are the native ones. Basically, you can replace some code with whatever's fastest on the current hardware. You can say, I have AVX 256, let's do some vectorization, and so on. The idea would be to have the performance of a source-based distribution like Gentoo in a binary-based operating system. That's a long time away, though, and for now, continuing from Felix's talk, I have created a SPU Mark II just-in-time compiler. It found various bugs in Thor, literally dozens, I believe, along with the backend. There's now 16-bit instruction support, and the register sizing is sort of, kind of, but not really implemented. So it's just sort of making it up in the backend instead. And it already has the automated test suite, similar to the one I mentioned about interpreting the RISC-V. This does basically the same thing for the SPU2. It's sort of a proof of concept to make sure the idea works. It runs the interpreter. I ported the interpreter, largely based on Felix's. I needed this for the test suite, so I just made a new one. One key difference from his is that there's a shared bus with the JIT. Instead of duplicating the code, all of the ROM loading, the logic to write and to read is basically shared between the two. Serial output and input, tracking memory, it's all one thing. It's specialized at comp time. So yeah, that allows deduplicating a lot of the code. And the one key feature about the JIT is it uses fast memory. All virtual memory is mapped into the host at a static offset, which means if something is in memory on the SPU as address 10, it's on the host architecture as address 0 by 10,000 hex plus 10, or 65,546. The reason I chose that offset and not 0, which I was originally going to do, is that I'm running a hardened kernel, which means that I am not able to map in memory by default at any address lower than 65,536. If I try, the operating system says you're not allowed to do that. This is for security reasons. If there's a bug in the kernel and it tries jumping to null, and I've mapped in malicious code there, it means that I now have kernel mode access, which is not something you want. I can actually override that and let myself put it at a lower address, but this is not a good idea for anything meant for other people to use. And it means I'd have to go to root every time I want to run this, which not a good idea, or every time I boot the system to run it. And yeah, that's basically all the slides I prepared, because for now I'm just gonna focus on the actual code and how things work. One quick example is the test suite. The way this works, it's running the interpreter and the JIT side by side, and this is emulating the first test that I have, 1.hex, running one instruction at a time, going over and over and over, and then just verifying if registers, verifying memory, and so on. That's the maze test that he was running. In order to avoid it being a mess, it's actually muting the interpreter first, so only the JIT is showing any output there. But yeah, it's the first file basically just wrong one. The first file prints out hello world and then does a busy loop printing out 1,000 exclamation points. This one can run at in about 5 seconds currently. Oh, is that the interpreter? That's the interpreter. Why is that the interpreter? Because it's configured wrong, probably. Doesn't matter. So yeah, what this is doing is it's running this it's running it twice at the same time. One instruction after another, after another, after another. The way the test works is it maps in the it sets up the JIT bus, it sets up the interpreter bus, sets up the actual CPUs, and then what it does forever until it reaches the target specified in the test definition, or it hits a specified limit saying you're not allowed to run that many blocks. It should be done by now. It will keep running both. It runs the recompiler, runs the interpreter, verifies that the registers match, verifies that the bus state is the same, which this measures, for instance, serial output. Meaning it checks that the same value is printed by both. For instructions that modify memory, it also checks it checks a couple instructions near the stack pointer to see that it gave the correct results. So yeah, it's able to check for any mistakes in the RAM, in the registers. It's able to just prove that the JIT has the exact same effects as the interpreter, not just internally, but on external state too. Easy to define. It's just you give it a file, give it how many instructions to run at a time, where to end, and it'll just keep going. For the test, it actually mutes the exclamation points because there's no reason to spew out 2,000 of those. So it just counts how many it did, keeps going up and up and up, and eventually the test finishes, test passes, goes to the next one, on and on and on. It gets to the maze, which doesn't actually succeed right now, but that's not the point. is timing. With the interpreter, one key idea here is to check how fast it's actually going. Because if it can't match if it can't at least outmatch the interpreter by a very large margin, then there's no real point. The generated code has to be at least somewhat efficient. Currently, the generated code is actually pretty bad in terms. It's not optimized at all. So with the interpreter in the fast mode, it's able to do that first test in 4.6 seconds. With the recompiler, which takes a bit longer to build because of course it does. Yeah, I'll just come back to that. So the way that the interpreter works is basically the same as the way that Felix's works. It goes over the instructions one at a time, reads values in from the bus, writes them out, and one notable Zig feature that he touched on that I actually took a step further. I have the CPU instruction structure defined. I literally just have it copied from his project. Condition, input, and so on as packed structure. Now, what his interpreter does, if I remember correctly at least, is to read an instruction, it fetches it from here. It reads it as a 16-bit value, and then it bitcasts it. I took that a step further. The read function I have is generic on the type. You give it the type to read. I didn't even plan it out this way. It was originally just so you could read between 16-bit or 8-bit. You give it the type to read and the address, and it will automatically read it as the correct type. Not worth a bitcast in it per se, but for the JIT at least, it literally just interprets the memory directly. It creates a pointer to it and just reads it. And that was a really neat feature. It's able to just give it the type and it works. You don't have to worry about the cast. It'll handle it correctly internally. Here we go. Now that this is actually built, the interpreter took 4.6 seconds. The JIT took 1.8, and this is still very inefficient code. It should be significantly faster, but it's currently not generating the smartest code by any measure. So yeah, the way that the interpreter works is straightforward. You check whether to execute based on the conditions. If you execute, you read in the inputs, and you generate the outputs, and it's just straightforward. The way that the recompiler works is slightly less so. First off, the biggest feature is the register allocator. Biggest not in terms of size, though that's probably true too. It's actually, it's a lot smaller now. Cleaned it up yesterday. What it does is it maps in registers or virtual memory to a RISC-V register, which is why it uses a U5 as the type, basically. There are 32 RISC-V registers, so it just uses U5 to mention to keep track of which one. It keeps track at all times of all 32 RISC-V registers, whether they're mapped to anything and whether they've been modified. Register, it goes over all of them, finds one that's not modified, and marks it as a temporary, and just gives it back. Otherwise, there's an error because there's not enough, but I don't think that's actually happened at any point. When you're done with the register, you give it up. It can store it implicitly. Getting a register is just straightforward. Go over the mapping, find one that's mapped to a virtual register, find the right ID. Getting it, do the same thing. It tries to get it. If it can't, it tries allocating a new one, marking it as the register. And if you told it to load in the value, I care what's in there, then it actually loads it in from the JIT's IP thing. It loads it in from the actual position counter in the JIT or whatever other variable register you're using. There's also a store used function which goes over all of them and just stores them one after another, and so on. These will be important shortly, but not just yet. To actually translate code is pretty straightforward. The instruction instruction pointer of the SPU Mark II CPU is statically allocated to the RISC-V X1 register, which means that it doesn't even need to be loaded in. It's just always there, which is pretty much just a micro optimization because it's used in literally every block. There's no reason to ever bother allocating it. For instruction count you give it, you tell it how many instructions you want it to translate. It will do that however many you told it. You can also tell it just keep going until you're done, until you hit a branch, in which by giving it null. So it reads in the instruction the same way the interpreter does. If it's in debug mode, it dumps out some useful information, what instruction it's translating, what the inputs are, and so on. And then we get to some of the more fun parts. Instead of being able to say, do I execute, the way the interpreter does, the way the interpreter works is it checks, is the condition true? If so, I want to execute. The way the recompiler works is kind of the opposite. Since it's generating code, it can't just check, is that condition true now? It has to check, is it true when this generated code runs? So it loads in the flag register to check, it loads that in through the register allocator. It sets aside a temporary, and when it's done with it, releases it. And then it basically generates some simple instructions. It generates an AND, which means that the temporary register now contains the first bit, what's the 0 bit of the flag register, and then it does a conditional branch. If that's 0, if it's false, then it jumps ahead by 2 plus the use count. The use count is however many instructions will be produced by a store use call, which means that this effectively jumps over from the start of the next instruction here, the load register. It jumps 1, store used, and 2. It jumps over this. One of the neat way this works is you give it an offset. The target is currently used as an offset from the current position in terms of the RISC-V instructions. So internally, this gets translated, this branch. The way this works is it creates a new label, generates the branch in the builder, and then adds that label in because it needs the label because it needs to know the current position that tracks where it started. And this basically tells it, okay, so when you get to that label, when you are generating this in the actual assembler, this is the target in terms of RISC-V instructions that you're going to want to go to. Then the Thor translator actually produces that correct value. I'll do that later. So yeah, and then, so what this basically says is, if that condition is true, jump over this bit here. What this bit says is, if the condition is false, we want to load the new position into the register, and then we want to store them all and jump to the exit. We're done. So basically what happens is, if execute is false, it exits the translated code entirely. Otherwise, it continues on, and that's true for all the other conditions too. It's the same thing, but with different values. Then for the actual instruction, if you're executing it, what it does is the 0 register, if the input is 0, it's just mapped to the RISC-V 0 register, which literally always returns to 0 on read and can't be written to. For immediates, it allocates the register, loads in the value. For the other options are peak or pop, which means you're getting a stack value. So it loads in the stack pointer, offsets it to the physical address with that 10,000 offset I mentioned. And then it does a load 16, which means that it takes that address and loads 16 bits from it into that register. If it's a pop, it then also modifies the stack pointer and continues accordingly, and marks it modified so the later store use cleans it up. It does the same thing for the second input to the instruction, and then for the output, it does the same work that the interpreter does, but it generates it instead. So for instance, if we're assign extending a value, which means that if the this is for the lower bit, right? Yeah. If the 8th bit is set, then it's negative. Otherwise, it's positive. It extends it the same way. All these instructions do the exact same thing. They modify register allocations, get all the work done. And then same thing as the interpreter. Based on the output, either we ignore it, we push it to the stack, or we jump over it. And that's basically it. The flags were modified, but everything is exactly the same. When we're done with the full translation, oh wait, that's actually done. The G is gone. If we haven't jumped anywhere, then we load the current position into the position counter, and then we store all the registers. This stores the PC, stack pointer, flags, and so on, updating them in the host effectively. Then it tells Thor, do all the heavy lifting now, which is sort of where the name came from, but not really. So Thor does all of the translation. It takes RISC-V, allocates it to the 64-bit registers, translates the machine code, assembles it, and does the mini linking. That one's not working, but I don't need it because I have this. That goes through here. And it basically just tells the assembler, go through the list of internal references and resolve them. That's not needed. It goes over the internal references and finds in the list of labels and inserts the addresses correctly, offset, and that's it. Then once all of that's done, once it's translated, what it does is it gives the result back to the host. It finds the physical address of the generated function and gives it back to the host. So which then has a cache for it. So it basically says, if we already have it cached, let's just run it. Otherwise, translate, run it, add to cache. And that's basically it. That's all there is to it. The actual, as Felix mentioned, writing an interpreter for this was straightforward. At most took an hour. It's really simple. The actual JIT was very similar. The only part that needed to be redone was the translator. The rest of it I was able to literally just copy from a different project I had. This whole thing's 600 lines, and it's very, very similar to the interpreter. The logic is all the same, just requires a slightly different method of thinking. One last neat feature to show off before I'm done is this. In order to load in a value, the way the interpreter does it, is it just directly calls the read function. But this can't do that because we need to read it in the generated code. What this function does is it generates a call to a function in the actual host code, not a generated call. You give it the list of inputs and outputs, and it literally generates a call to these functions. They have to use the C calling convention because it has to correctly support inputs and outputs. You can't use structures directly, only pointers currently, because those can just be passed as integers. But it reads in the value. This function returns it to the call down here. This just automatically does the correct thing. It calls the function up there and handles the results correctly, and you can even tell it where you want the output. Give it to me in register 0, give it to me in a temporary, give it wherever, and it'll just work. So yeah, that's basically it. What I was going to say though is the interpreter took maybe an hour to write. This took basically the same amount of time, but adding in all of the support for it and the back end took much longer. Correctly supporting shifts, translating those to the AMD 64, everything. I think there were like 6 or 7 instructions that were completely done from scratch in here. Needed to support saving the results in the calls because I hadn't bothered doing that yet. Required reworking the register allocator so that it could actually handle so many input registers, because before it would just crap out after like 5 of them because it never bothered throwing them away. So there was a lot of work that had to go into the backend. But now that that's done, writing in the main goal of this was achieved. Writing an emulator using the JIT is almost exactly as straightforward as writing the interpreter, and significantly faster. And while it might not have looked as fast when running the tests, because when running the tests, it was running the interpreter and the JIT at the same time. When running just the JIT like this, it takes 0.7 seconds, whereas the interpreter doing the same thing running the same thing takes a mere, or should I say, it takes not a mere, takes more, takes a more. It's about twice as fast. And this is with bad code generation. One of the advantages of this architecture is I don't have to actually touch this at all. I don't have to touch the translator. This code is more or less fine. There's a couple changes that need to be made, but for the most part, it's good. But if I just make improvements to the back end, which the front end doesn't even need to know about, it'll just start being faster out of the blue. Or one other example would be cache with the, I'm not even going to bother recompiling, I'm just going to scroll up. When running this maze with the JIT, it's running, what, zeros, 20 million instructions approximately. And there are 107 cache misses, which means since every time there's a cache miss, it adds the value to the cache. What this means is that by the end of it, there's 107 entries in the cache. So finding some arbitrary block means going over all 107 of them at worst case, an average of 50. Improving how the cache behaves would probably reduce this to 400 milliseconds. Improving the generated code would probably get it down closer to 200, if not 100. This could probably get below 100 milliseconds with a few days worth of work. And none of that requires touching the translation, which means that it's modular. All of the stuff is simple. Like calling a function like this, completely simple. You don't have to do anything except tell it what function to call, what you want to pass to it, what outputs you want. You can give it raw numbers. You can give it registers. It'll just always do the right thing. Self here is a pointer. It's a pointer in the host. It just works. It automatically does the right thing. So it meets the simple goals. It's fast to translate code. It's fast to run the code. So it meets those goals. And going back up to the top, it's usable for emulation, and it is usable for compilation, though I don't actually have that hooked up yet. The same assembler that generates the code for the emulator that generates the host code, you can just take that. You can give it a different offset, take the code it produces, and dump it to a file. There's no optimization passes yet. Those are going to be coming up soonish. Backends, there's still only really one. Everything is very, very simple. It's performant. You can control it completely. If you want to change how it generates code, if you want to control, for instance, if you want to control what API is used, that's going to be possible too, though I didn't implement those yet. Anything you want to change, you can do that. And it hits the modularity goal. The JIT, the translator, is completely independent of the actual backend code. It's independent of Thor. All of these pieces work together, but you can use them on their own too. You don't need to keep them together. And that's about it. So, yeah, that's it.
Okay, thank you, Noam. Do you want to share maybe some links to your project?
Yeah, sure. Let me pull that up. Currently, I'm using SourceSet as the host because it works and is actually nice, and I'm not just saying that because I'm technically interning for it right now. So yeah, if you look on SourceSet, it's very easy to find. It's probably the only thing spelling simple with a C. So yeah. All the sources are in one place. There's an LLVM-IR parser. I didn't actually mention this one yet, but I don't have the generalizer yet, but it's able to parse in the IR completely and has a very basic backend for another ISA called LIM. It has the recompilation engine Thor, Tricitrix, which is the other emulator I mentioned. That's the architecture that this one currently targets. Yeah, and everything is there. And if this bug tracker gets any actual usage, that would be nice. But yeah, I can post the link in the chat if you want, but that would mean opening it, so...
I think somebody else posted already links. I posted those. Yeah, I asked you for the links so that they can also stay in the video, in the recording. So let's switch to the Q&A view then. Just as a reminder, if you want to ask a question and you want to make sure I see it, please tag me in it. So let's start with the default question. So how did you find out about Zig, and how long ago was that?
I don't actually know. I know how I found out about it the most recent time when I actually got into it. But I actually think I saw it 3 or 4 times before that through various links. I think people posted in some chat rooms I'm in. I'm not 100% sure. So yeah, I don't really know how I found it. I think there was I found I found the either the Raspberry Pi bare metal thing Andrew wrote or one of the operating systems kernel. Someone had a partial kernel written in Zig. I think I found that by accident, and that's how I found the language. I think something along those lines.
Okay, so we have already a couple of questions. First of all, what is meant by proof and trust? You mentioned these two terms during the presentation, and why would you want it?
Yeah. The trust thing I mentioned actually is I brought up the trusting trusts thought experiment basically, which is if you have the original idea is if you have a malicious compiler, which does when you're compiling, for instance, the login manager, it generates malicious code letting someone enter with a static password no matter your account, and when compiling a compiler, it inserts its own malicious code into it. The idea is if you can't trust the original one, you can't trust a compiled compiler with it, no matter how clean the source code is. The idea behind it is even if you can look at the source code, you can't verify that the behavior is correct because it's possible that the compiler that you're using is doing something malicious. The same idea applies here. When I'm talking about proving correct, what I'm basically saying is if I'm making an optimization to the RISC-V code, I need to be sure that the behavior before and after is exactly the same. I don't necessarily care about the actual internal details. I don't care about registers or emulated memory or anything along those lines. What I care about there is if I'm writing some Zig file.
By the way, sorry, Noam, if you're showing, let me know if you're showing something on the screen so I can put up the right view.
Yeah, I will right now. Yep.
Okay, let me switch then. Sure, go ahead.
I'm writing some Zig code, whatever it happens to be. I want to be sure that if I have a variable here, if there's a loop optimization, it's not going to result in the variable having the wrong value. I need to be sure that the optimization is improving the efficiency of the code without changing the results. So the idea of proof there is if I can interpret the RISC-V before and after, I can map these variables to the RISC-V registers. I can say, are the values changing? Are they correct for the values that are resulting? So if I'm changing, for instance, let's say you have, this is not C. Let's say you have some value, and you're doing something like this. You're adding something like this. That's outside of a function, so CLS is complaining, but that's not really important right now. If you do something like this, if I'm optimizing this into, if I'm turning this from, or rather, let's say I'm doing this, because this is easier to exemplify, that's the wrong word, to make an example out of. If I'm adding 3 and then multiplying by 4, well, let's say I just change that into add 12. I know both values. I want to be able to make sure that the compiler isn't generating the wrong number here. I want to be sure that the compiler isn't messing that up somehow. For something trivial like this, that's not really a concern. But for a lot of optimizations, they do often have negative effects. It's the same way that, or another better example would be GCC's -O3. If you're giving it the highest optimization level, it can sometimes produce the incorrect code. Or not necessarily incorrect, as much as not what you intended. If your code isn't 100% perfect, the optimizations will make the wrong decision. They will assume values are present that are not, and they will do the wrong thing. They will also sometimes result in slower code. So one example of what you could do here is you could verify, is this actually making it faster? You could say, if I'm interpreting this RISC-V, how many cycles did it take interpreting it before the optimization, how many did it take afterwards? Did it actually make it faster? And if not, you can just ignore and discard the optimization entirely. So that's the basic idea behind provability. If you can prove that the result matches the input, then it means that you can actually more or less trust your code. It's similar to Rust's idea of safety. If you can prove that this code, the idea behind Rust safety, as I understand it, is you need to be able to prove that the code is doing exactly what you tell it to. Rust does that with the borrow checker. It's a tool that you use to make sure your code does what you think it does. There's similar concepts elsewhere. You can say, for instance, Zig has its runtime safety checks and so on. The idea here is to basically move some safety checks to compile time. Because, as we all know from the Zig of Zen, compile errors are better than runtime crashes. If you can prove that the code is correct, you can avoid both of those. And if the code isn't correct, if there's something wrong with the compiler itself, better for the compiler to tell you, hey, there's something is wrong, than to silently give you the wrong output. That's the general idea there.
Okay, thank you. Another question. This is from K-Proti. Let me know if it makes sense or if we need to ask him to reformulate. But the question is, will the RISC-V IR support native instructions that aren't representable in the IR directly as an ISA-specific instructions? As in ISA-specific instructions? You're muted, by the way. Okay, now I can hear you. Yeah, please continue.
That's an interesting concept. The problem there is one of the key goals here is to be completely platform independent. If there are ISA-specific instructions that aren't supported by the actual backend, the correct option there is generally add it to the backend, teach the backend about it. But I can see how in some cases it could be useful to have sort of like an inline assembly type thing there. About that, there are some trade-offs to be considered there.
There's a question from Felix. Are you prepared for implementing the MMU for SPO Mark II emulation?
It'll be fun. I mean, all of the bus code's in one place still. So it would basically just be a modification here. The actual recompiler shouldn't be affected by it at all.
Okay. I think we have got all the questions. Well, thank you very much. That was also an awesome presentation. I think we can move now towards the end of the show then. Thank you again, Noah. I hope to hear from you again in another session in the future.
Hopefully next time it'll be on stage 2, because I plan on getting back to that very soon.
Awesome.